Hello everyone. In this session, let us discuss about types of semiconductor. In the last session, we saw the basic structure of an atom, energy band diagram, the classification of solids based on energy band diagram. That is, according to energy band diagram, these solids are classified into conductors, semiconductors, and insulators. In conductors, there is no forbidden energy gap between valence band and a conduction band. In insulators, there is a large energy forbidden energy gap between the valence band and the conduction band. It is around 5 electron volts. And in semiconductors, there is a small forbidden energy gap of 1 electron volt between the valence band and the conduction band. And we also saw the different properties of semiconductors. And let us discuss with the different types of semiconductors. These semiconductors are broadly classified into two types: intrinsic semiconductors and extrinsic semiconductors. And these extrinsic semiconductors are furthermore divided into p-type semiconductor and n-type semiconductor. Let us first try to understand what exactly is the meaning of intrinsic semiconductor. The semiconductor in its purest form is called as intrinsic semiconductor. I already told you the examples for these semiconductors are silicon and germanium. If I am going to consider only the silicon or the germanium atom, then that will be called as intrinsic semiconductor. Any particle containing only the silicon atoms or only the germanium atoms are called as intrinsic semiconductor. That is, semiconductor in its purest form, without adding any kind of other atoms, without adding any kind of impurities, is called as intrinsic semiconductors. So, how does this intrinsic semiconductor behaves when it is led to conduction? That is, conduction in intrinsic semiconductors. At low temperatures, all of the valent electrons are tightly bound to the nucleus. I mean to say, we have already seen in the last session, that is, four number of valence electrons are present in both germanium as well as silicon. Germanium is denoted by Ge and silicon is denoted by Si. In both of these semiconductors, there are only four valence electrons, and these four valence electrons will form the covalent bond with its nearest four other silicon atoms. In order to form a covalent bond, two electrons are required. So let us try to understand that with this simple diagram. I am having one silicon atom which is having four valence electrons. Nearby I am having another silicon atom which is having four valence electrons, and all of these silicon atoms will be surrounded by similar type of atom, that is similar type of silicon atom, each having four valence electrons. So if I am going to look into this part, here I am having one valence electron, that is this one from this silicon atom, and this valence electron from this silicon atom, and these two valence electron can be together form a covalent bond. This itself is called as a covalent bond. Here again, this is a covalent bond. Here, if I am going to consider that there is another atom which is having valence electron, then this will be a covalent bond. This will be a covalent bond. So each silicon atoms will be bonded tight together in order to form a covalent bond. The same kind of structure is found in this diagram. Here, according to this diagram, I am we are seeing an empty space over here, and that empty space is called as hole. We have already discussed about this. And this empty space or a hole which is created in an orbit, that will be having positive charge. So hole is an empty space which is created in the orbit. How these holes are created? I already told you that these semiconductors will behave both as a conductor as well as an insulator. When I am not going to provide any kind of external energy, these semiconductors will behave like an insulator. When an external energy is provided, the valence electron will absorb that external energy and will become a free electron, leaving an empty space and that empty space will be called as a hole, which will be having positive charge. So in this particular diagram we are having a hole, and we are having a covalent bond and thermally ejected electron, and these thermally ejected electrons are called as free electrons, which are responsible for the conduction of current. At lower temperature, there will be no free electrons generated, or there will be no free electrons created in the crystal lattice structure. So at lower temperature, these semiconductors will behave like a perfect insulators. Now let us see what happens at higher temperature. Whenever the temperature of these semiconductors are increased, electrons present in the last orbit, if I am going to consider this as the nucleus and this as the outermost shell or the outermost orbit, then in semiconductors we will be having 4 valence electron. Now I will start to provide external energy. Let me consider that I am providing the external energy in the form of heat. Now what happens is the electron which are present in the outermost orbit absorbs that energy, and that energy will jump. If I am going to consider this electron will jump from the valence band, and now it will become a free electron. But here an empty space will be created. This was the last orbit, but now an electron is missing, and that electron space now will remain empty, and that empty space will be called as a hole, which is having positively charged. Because of this, there is a deficiency of electron in the covalent bond, because one of the electron has jumped from the valence band to the conduction band, leaving an empty space, and that empty space will create a deficiency of electron in the bond structure, right? And these free electrons are now responsible for the conduction of current. With the application of these external energy, not only the free electrons will start moving from one place to another place, which leads to the conduction of current, these holes which are positively charged are also having the capacity to absorb the opposite charge, which are freely roaming near the atom. This need not be the same electron which have just jumped from the valence band to the conduction band. There can be any other electron which is called as a free electron, and even that can get attracted towards this empty space. Or if you look into the crystal lattice structure of these semiconductors, the deficiency of electron in the covalent bond created a hole which is positively charged, and this hole might attract the nearby electron. In this way, the electron have jumped from this place to this place, whereas the hole have jumped from this atom to this atom. That is, electron have jumped from here to here, whereas hole have jumped from here to here. So meanwhile, we can see that both electron as well as holes are moving in the opposite direction. So the total current will be equal to the sum of the current which is generated because of the electron, that is denoted by IE, and the current which is generated because of the movement of holes, that is denoted by IH. So the total current IT will be equal to IE plus IH. So what exactly is this intrinsic semiconductor? Semiconductor in its purest form is called as intrinsic semiconductors, and the examples are silicon as well as germanium. No impurity atoms will be added for these semiconductors, and at lower temperature these intrinsic semiconductors will behave as a perfect insulators, and as the temperature increases, as we add energy externally, these semiconductor will start to behave like a conductor. Now let us see what exactly is the meaning of extrinsic semiconductor. Extrinsic semiconductor in the sense a pure semiconductors doped with impurity atom is called as extrinsic semiconductor. So what is this doped in the sense? Adding the impurity atom. Doping in the sense adding the impurity atoms. For intrinsic semiconductor is nothing but the semiconductors in its purest form. Extrinsic semiconductors are nothing but pure semiconductors. We are taking a pure semiconductor, and for that pure semiconductor we are adding impurity atom. in order to increase the conductivity of that semiconductors, and that will be called as an extrinsic semiconductors. Now, what exactly is this doping? The process of adding small amount of impurity atom to a pure semiconductor is called as doping. The added impurities are called as dopants. So, why does this doping process is done? Doping is done in order to increase the conductivity of these semiconductors. And these extrinsic semiconductors are broadly classified into N type of semiconductors and P type of semiconductor. Now let us see what exactly is the meaning of these N type of semiconductors. N type of semiconductors are obtained by doping pure semiconductor with a pentavalent impurities. Pentavalent means an atom which is having 5 valence electrons. That is, in the last orbit of an atom there are 5 number of electrons. Penta stands for 5. So we are going to add atoms which are having 5 valence electron to a pure semiconductor. That is, to silicon and germanium, we are going to add atoms which are having 5 valence electrons, and such atoms are antimony, arsenic, phosphorus, etc. So, the pentavalent dopant atoms are also known as donor atoms or donor impurity because it donates a free electron to the pure semiconductor. In silicon and germanium, we are having 4 valence electron. In these impurity atoms, let me consider an example of arsenic. We are having 5 valence electron. In order to form a covalent bond, we need 4 valence electron. So out of these 5 valence electron, 4 of them will be used in order to form a covalent bond with its neighboring silicon atoms, and the fifth electron will be set free, and that fifth valence electron of the arsenic will be called as a free electron. So if you look into the diagram, we are having a lattice structure where we are adding arsenic as a impurity atom. The 4 valence electrons of arsenic have formed the covalent bond, formed a 4 covalent bond with its neighboring silicon atom. Whereas the fifth electron is set free, and that fifth electron is called as a free electron. If I am going to add one arsenic atom, one free electron will be created. If we are going to add 1000 number of arsenic atom, 1000 number of free electrons will be generated. So, with the impurities added, the number of free electrons will increase. If the free electrons are increased, then with the application of external energy, these free electrons will start to move from one place to another place, leading to the conduction of current. So, these arsenic atoms are called as dopants, which are having the capability to donate the fifth valence electron to the semiconductor. These are called as donor atoms or donor impurities. And here we are going to see that free electrons are more in number, electrons are the majority charge carriers, and holes are minority charge carriers. With the application of external energy, we can see that more and more number of free electrons are created, and these free electrons are responsible for the conduction of current since they are more in number compared to holes, that is the empty space which is created in the orbit. These electrons are called as the majority charge carriers, and holes are called as the minority charge carriers. If we are going to talk about the arsenic atom, arsenic will be having 5 valence electron. Arsenic will be having 5 valence electron, out of which 4 will be used to form a covalent bond with its neighboring silicon atom, and the fifth valence electron will become a free electron. Now, but as soon as the external energy is supplied, these free electrons starts moving from one place to another place. Now, there is a deficiency of electron in this arsenic atom. Deficiency of electron in this arsenic atoms in the sense, on a whole, the atom will be neutrally charged. Neutrally charged in the sense, an atom will be having central nucleus surrounded by a number of orbits, and in the orbits will be having electrons which are negatively charged. In the nucleus I will be having positively charged particles which are called as protons. Surrounding the nucleus will be having negatively charged particles which are called as electrons. There will be equal number of positive and negative charges. That is, the number of protons inside the nucleus will be equal to number of electrons outside the nucleus. So the charge will remain balanced, and now the atom will be in the neutral state. The atoms will not be having any kind of charges, so the atoms will be neutral in charge. But here in this n type of semiconductor, in case of an arsenic atom, the fifth electron will be lost. The 4 valence electron will form a covalent bond with its neighboring silicon atom, whereas the fifth valence electron will become free electron. Now there is deficiency of electron in the arsenic atom, but inside the nucleus I am having the positive particles, that is proton number are same, but the electron number outside the nucleus is decreased by one number. Let me consider that there is one hole created in the arsenic atom. So now the positive number of charged particles is more compared to negative number of charged particles. Now the atom will no more be neutrally charged, it will be having a positive charge. Now the atom will hold a positive charge because atom is having more number of positive charges compared to the negative charges. Now this atom will be called as a immobile ion or a donor ion. An atom has lost an electron in this arsenic case. Now this atom will be called as an ion. So this is called as a donor ion because it has donated one of the electron to the semiconductor. That is, one of the electron is being donated to the crystal lattice structure. So it is called as a donor ion, and these ions will be immobile, that is it cannot move because it is being tightly bonded with its neighboring silicon atoms. So what is this n type of semiconductor? N type of semiconductors are obtained by adding impurities to the pure semiconductor atoms. Pure semiconductor atoms के pentavalent impurity atoms na add ಮಾಡಿದ್ರೆ will be getting n type of semiconductor, and the example for pentavalent impurity atoms are antimony, arsenic, phosphorus, etc. With the addition of these pentavalent impurity atoms, more number of free electrons will be created, which leads to the conduction of current. And these excess number of free electrons are responsible for the conduction of current, and these n type of semiconductors will be having more number of free electrons. Here in the n type of semiconductor, electrons are called as the majority charge carriers and holes are called as the minority charge carriers. Now let us see what exactly is the meaning of p-type semiconductors. For the same semiconductor, if we are going to add trivalent impurity, tri stands for 3. What is the meaning of trivalent? An atom which is having 3 valence electrons is called as a trivalent atom. So in order to get a p type of semiconductor, we are going to add trivalent impurity atom, and the examples for trivalent impurity atoms are boron, aluminium, gallium, etc. And these trivalent impurity atoms are called as acceptor atoms or acceptor impurity, because if I am going to consider an example of boron, boron is having 3 valence electron, and in order to form a covalent bond with its neighboring silicon atoms, it needs 4 valence electrons, right? All of these covalent bonds will not be completely filled. There is an empty space in the boron because this boron is having only 3 valence electron, and this fourth covalent bond is incomplete because there is no valence electron, fourth valence electron in the boron. So there is a creation of hole, that is an empty space is created. An empty space will be called as a hole, and that empty space or a hole will be having positive charge. So with the addition of these boron, the number of holes will be increased in the crystal lattice structure. So in p-type of semiconductors, we can easily tell that holes are the majority charge carriers and electrons are minority charge carriers, because just now at the starting of this session we just discussed that the electrons as well as holes movement both are responsible for the conduction of current. So in the p-type of semiconductor we can see that hole number are more compared to electron number. So holes will be considered as the majority charge carriers and electrons will be considered as the minority charge carriers. And these holes, as I've told you, are having positively charged and electrons are having negatively charged, and these positively charged holes are having a capacity to attract the negatively charged electron. They are having the capacity to accept the electrons. So these trivalent doping atoms will be called as acceptor atoms or acceptor impurity. Whereas in the N type of semiconductor, whatever the impurity atoms we are adding, they will be generating one number of free electrons to the crystal lattice structure. So they are called as donor atoms. Whereas here in the N type, P type of semiconductor, the impurity atom, whatever is added, will be creating a hole in the covalent bond, and that hole is having a capability to accept an electron from its neighboring covalent bond or neighboring silicon atom. So these trivalent impurity atoms are called as the acceptor atoms or the acceptor impurities. So in this session, we saw the different types of semiconductors. That is, these semiconductors are broadly classified into intrinsic semiconductors and extrinsic semiconductor. Intrinsic semiconductors are nothing but the semiconductors in its purest form. Extrinsic semiconductors are nothing but the semiconductors in which the impurity atoms are added, and these extrinsic semiconductors are furthermore divided into N type and P type of semiconductors. So let me conclude this session at this point. In my next session, I'll be dealing with a new topic. Thank you.